Here's problem 2013. A 5-gram coin is dropped from a 300-meter building. If it reaches a terminal velocity of 45 meters per second and the rest of the energy is converted to heating the coin, what is the change in temperature in degrees Celsius of the coin? The specific heat of copper is 387 joules per kilogram per degree Celsius. There's a couple of ways to think about this problem. Let's think about our change in energy mechanically. That's going to equal our change in potential energy plus our change in kinetic energy of the coin. Change in potential energy would be our final potential energy minus our initial potential energy. And for that matter, our change in kinetic energy would be our final kinetic energy minus our initial kinetic energy. Our final potential energy is going to be 0, while our initial potential energy would be mgh. Our final kinetic energy is going to be 1/2 mv squared, while our initial kinetic energy when we first dropped the coin was 0. We start from rest. We reached a terminal velocity, which means our velocity continued to be constant after we reach that value, and hence we'll have a final kinetic energy of 1/2 mv squared. Let's calculate this. This is going to be a negative. We have a 5-gram coin, 0.005 kilograms, 9.8 for G, a height of 300 meters. And then we have a coin, 0.005 kilograms, final velocity 45 meters per second, square that. If I calculate this, what do I get? 0.005 times 9.8 times 300. Negative 14.7 for our change in potential energy, plus 5.06 for our change in kinetic energy. This will give us a total change of a negative 9.64 joules mechanically. But we should know that this is a rather isolated system as we're looking at it. Our change in energy mechanically plus our change in energy thermally should equal 0. So it should be true that our change in energy thermally will equal the negative of our change in energy mechanically. Or negative 9.6 would be a positive 9.64 joules. And hence, we should have that the mass times the specific heat. We're going to use copper for this coin, so we'll assume it's a copper coin, times our change in temperature will equal 9.64 joules. So our change in temperature will equal 9.64 divided by the mass, which was 5 grams, 0.005 kilograms, and the specific heat, which is given as 387 joules per kilogram per degree Celsius. So 9.64 divided by 0.005 divided by 387 is 4.98 degrees Celsius. So our change in temperature of the coin will be about 5 degrees Celsius. It will heat up that much. That's one way to think about it. Probably an easier way to think about this is as this coin is dropping, we're going to have energy available mechanically due to that. And our energy available is going to equal our potential energy minus the energy that went into the kinetic energy. So that's going to equal mgh minus 1/2 mass velocity squared after we reach that terminal velocity. So this would be 0.005 times 9.8 times 300 minus 1/2 times 45 squared, and that will give us the 9.64 joules. So that is the energy that's available. All this energy will go into internal energy of the coin. In other words, our change in internal energy of the coin will equal the heat added plus the work done on the coin. Now, we have this coin of specific size, and the volume of this coin is not going to change a whole lot, even as we change its temperature. So the work done on the coin, in a sense, will be zero in this sense, and all this energy will go into the change in internal energy due to the heat added to the coin. So the mass times the specific heat of the copper times the change in temperature will equal this 9.64 joules. The rest of it follows as before. Our change in temperature will be 9.64 joules divided by 0.005 kilograms, 387 joules per kilogram per degree Celsius, and that gives us 4.98 degrees Celsius. So just an alternate way of thinking about the problem, maybe a little bit easier to think about it conceptually that way. Either way, our change in temperature is about 5 degrees Celsius for the coin.